Hey. Sure. Yep. Yep. Okay. Yeah, that's all right.
Shall we start?
Yep. You can start.
So, greetings everyone. I would like to welcome our speaker, Dr. Devansh Agarwal from West Virginia University. It is an honor for Parsec to host a talk by him. Thank you so much for accepting our invitation. Dr. Devansh Agarwal is an alumnus of IISER-TVM from batch 10. He is one of the founding members of Parsec. He just completed his Ph.D. from West Virginia University. He has developed real-time data analysis pipelines with Python and CUDA for time series data for from three of the world's largest radio telescopes. He has also created an open source Python package model which has led to discoveries of 100 plus astronomical signals. Dr. Devansh Agarwal has collected and processed 800 plus terabytes of data of time series searching for astronomical transients. He has also headed a team of 20 astronomers around the globe to search for host of astronomical transients. He has published 16 articles and presented his research at 6 different conferences. His research includes the usage of GPUs and deep learning to accelerate astronomical discoveries. Now I would request Dr. Devansh Agarwal to continue with the talk.
Yeah. Thanks for that introduction, and thanks for having me. Well, so how do you want to do this? So you said that this the talk section, and then you want me to talk about, I guess, my journey, I guess, with IISER and after IISER.
Yeah.
So how do you want to do it?
We can start with the talk, then for some time we can discuss the journey, and then I guess we can take some questions if there are any.
Okay, sure. And so just sort of curiosity, what year are you guys in? Like, is it a mix of, I don't know, first, second, third, fourth, fifth, everything, or how's it?
So many of us are from third years and second years. I
Okay.
guess fourth and fifth years have also joined, but first
Okay.
years haven't yet joined the institute.
Oh yeah. So you guys are in IISER now, all of you?
Yeah, and
Okay.
also some are some are not from IISER.
That's fine. Yeah, that's okay. Alright, so right. So can you guys see my screen?
Yeah.
Can you can see it?
Yeah.
Well, all right. So, well, the title of the talk is "Fantastic Bursts and How to Find Them," and it's sort of taken from J.K. Rowling's Fantastic Beasts and Where to Find Them. I've changed 2 words. One is beasts to bursts, and the second thing is where to how. And so go into why we have done that, and what's there on the background is the Green Bank Telescope over here in West Virginia. So it's a 100-meter telescope, which collects all the radio waves, and then we use that to do our searches with it. Now, at any point in the talk, if you think that something is unclear, just feel free to unmute and ask me. The other thing which I want to clarify is I tend to get really excited when I talk about this topic, and as a result, I start speaking really fast. So if you cannot follow, just unmute and just say, "Hey, slow down," or "Can you repeat that?" or something like that, and I'll be happy to sort of go over something and go over slowly. Okay, so let's start now. For the rest of the talk, we'll be using data from the radio telescopes. And here on the left-hand side, we have the Parkes Radio Telescope in Australia. So this is a 75-meter dish, and that's the receiver on top. And all the data comes in, it goes into a device called spectrometer, and you don't have to worry about how it works and so on. But what it gives you at the end is a two-dimensional array, or something like this. So you have time, but you also have frequencies. So for each frequency channel, as we call it, you have a time sample. The number of frequency channels are typically of the order of 1024 or 4096 or something like that, which is 2 to the power 10 or 2 to the power 12, or something like that. And then you just point your telescope at some part in the sky and start recording this data. So the sampling interval, that means you take a sample every about 100 microseconds. So if you're observing for 1 millisecond, you'll get 10 samples, and if you're observing for 1 whole second, you will get 1,000 into 10 10,000 samples. So pretty soon you'll have huge amount of data just because you're sampling really, really fast. And then, as I told you, you have about 1,000 frequency channels or something. And these frequencies are in megahertz. So we observe at about somewhere between 400 megahertz to about 20 gigahertz. So you can choose any band in between, more or less, with all the telescopes, which we'll be talking about. And that's what you have. So this is our data. It's a two-dimensional array. You have frequency on the x-axis, time on the y-axis, and all these searches and everything is done on this data. Now, the other thing which I want to clarify, which is going to be sort of essential for this talk, is two astrophysical quantities. One is flux and the other is luminosity. So flux is defined as energy you are receiving per second per unit area. And in radio astronomy, what we do is we define the unit called Jansky, which is JY. And 1 Jansky is 10 to the power minus 26 watts per meter square per hertz. And the reason we have to do it is because radio signals are really, really faint. So you cannot keep just putting 10 to the power minus 26 everywhere. So you just define 1 Jansky as this, and everything is then measured in Janskys. So the flux of, if you point your telescope at sun, and if you observe at this frequency, which is 2.8 gigahertz, the flux of sun is about 10 kilo Jansky. So that's how we measure all the, or this is like how bright an object is, and just quantifying that. And sun, as you know, it's fairly bright in optical itself. In radio also, it's about 10 kilo Jansky. Now, flux is something which you see at the telescope. The other quantity is, which is a bit more astronomical than flux, is luminosity. And luminosity is something which is at the source. So if you have a source which is at a distance d, your luminosity is assuming that your source is emitting. So if it's so for example, for sun, it's emitting in all directions. So that's why you have this 4 pi d square in front. That's the surface area. Okay, and then F nu is the flux which you observe. So luminosity is independent of distance, because what you do is you put in distance here, you see how much flux you are receiving, and then you assume that that's the same amount of flux it's emitting in all directions. So you integrate over that. That's why you get the 4 pi d square, and that's luminosity. Okay, so these are two astrophysical quantities which we'll be talking about, mostly about flux, but I'll tell you where luminosity comes in, and we'll see how it goes. So first there were pulsars, and the title of the talk is Fantastic Bursts. And what we mean from fantastic bursts in this context is fast radio transients. These are transient objects. That means there's a very specific amount of time for which these guys are on, and these are extremely fast. So first there were pulsars. These were discovered in 1967 in UK by Jocelyn Bell. And these are essentially remnants of dead stars. It's actually a neutron star which has this lighthouse-like emission, and whenever this cone of emission passes your line of sight, you actually see this blip in your signal. So if you actually see in that 2D frequency time, you'll see this blip whenever you have pointed your radio telescope at a pulsar. And this was 1967. Since then, about 35 years, or actually 40-ish years. Actually, no, even 50 actually. Yes, it's 50. It's about 50 years since we discovered pulsars. We have discovered about 2,800 pulsars till date. Okay, and the rotation period, since it's a rotating thing, the rotation period at which these pulses come, they range from somewhere about 10 milliseconds to about 10 seconds. So there's a huge variety in pulsars. You'll see pulsars which give you a pulse every second. You'll see few which will give you pulses every 10 milliseconds, and then there are slow ones which will give you pulses every 10 seconds or so on. So these are pulsars, and the typical widths, the pulse width over here, which is sort of how long this or how wide this cone of emission is of the order of like 10% of the period or 5% of the period. So if your period is about 10 seconds, the 10% of that will be about 100 milliseconds. So that's fast. You have something which is astronomical, which is giving you a signal only for few hundred milliseconds or few milliseconds, and hence the term fantastic burst and the fast bursts over here. Okay, now on the left-hand side, what I'm showing you is the Crab Nebula, and Crab Nebula actually hosts a pulsar in it. So when astronomers actually pointed their telescope at Crab Nebula, they found pulses from the nebula. And what I'm showing here on the right-hand side is the frequency time, same two-dimensional array which we talked about. Here's the frequency, here's the time. And this signal over here is that blip which we talked about. But as you're observing at multiple frequencies simultaneously, you will see that blip on all frequencies. But the thing which you should notice over here is these are not aligned. Higher frequency blips or higher frequency emission arrives earlier than the lower frequency emission. So this is 420 megahertz, this is 430 megahertz, and the 430 megahertz signal has arrived earlier as compared to this one. And this happens because of a phenomenon called dispersion. So this is very, very similar to what happens when you shine white light at prism. Different frequencies travel at different velocities in a medium. Okay, and because of that, because of different velocities, you have different different velocities happen because of different refractive indexes for different frequencies, because refractive index is a function of frequency always. But anyway, same thing happens with radio waves as well. You have free electrons in the medium. This is the medium which is sitting between the pulsar and Earth, and because of those free electrons, waves undergo dispersion. And the way we see it here in our data is that higher frequency waves arrive earlier as compared to the lower frequency waves. So here is some pulse from a pulsar. Here is the higher frequency component. This is 1.8 gigahertz. This is about 1 gigahertz over here, and higher frequency emission comes earlier as compared to the lower frequency emission. This relationship of time delay between two frequencies, nu1 and nu2, can be quantified using this relation. So the time delay is follows an inverse squared law. So this is that inverse squared white lines which sort of tell you what you should expect. Now, this dispersion can be quantified using this quantity called dm, or dispersion measure. This tells you how many electrons you had along the line of sight or between you and the pulsar. So the dispersion measure is given as the integral of your electron density or NE, and integrated over where you are versus where the source is. So what we do is to observe these things, what we do is we de-disperse our data. We know with this relation that how frequency and times are related. So if you take your data which looks like this is higher frequency, this is lower frequency. If you add it all up, you'll get something like this. If you add all the frequencies, this is what you will get. But since you already know what the relationship between your time delay and a particular frequency is, you can correct for it. So you can roll your data. This is just a two-dimensional array, so you can just simply roll it and then add it up, so you will get a much stronger signal. So that's de-dispersion. So that's something which you have to do for all astrophysical radio transients at least. So whenever you have to observe them, you have to de-disperse your data first and then sort of do anything with it. Now, this dispersion measure is used as a proxy for distance. So this on the right-hand side is the map of electron density map of our own galaxy. So we know how the electron density is in our galaxy. This is Milky Way. These are the spiral arms of the Milky Way. And we are located somewhere over here at about -8.5 kpc in the y direction. This is where we are. You observe a pulsar, you'll see something like this. You'll see this higher frequencies arriving earlier as compared to lower frequencies. And since you're observing it, you know how to correct for it. And that will give you the dispersion measure. You know the electron density from our own galaxy. You know where you are sitting. You know where you are looking at. And then you can just integrate. So if you're sitting somewhere over here, you can just start integrating from here. Let's say you were looking in this direction. You can keep integrating until you reach this value of Tm. So that means you can get a measure of distance using the dispersion measure. So that's something which you can keep in mind, that dispersion measure is used as a proxy for distance. Now, for about 30-35 years, people were searching for pulsars, and then McLaughlin and al. Here at West Virginia University found these things called RATs. These are rotating radio transients, and here are two of the pulses from RATs. This is again higher frequency, lower frequency, and higher frequency arriving earlier than the lower frequency. And the top one is after you de-disperse and add all the frequencies. This is what it looks like. Now, what was different about RATs was, unlike pulsars, they do give you emission, but sometimes they do not give you emission in between. So you do not get a regular blip every, let's say, 1 second or 2 seconds. What you get is in an hour worth of observation, you'll get just 1 or 2 blips or something like that. So these are rotating radio transients. We do not know what exactly leads to this thing, that you only see some of the emission, not all of it. But anyway, these are RATs, and this is another class of transients which we observe using our radio telescopes. And then finally, coming to fast radio bursts. So this is where most of my work has been for last about 4-ish years. So let's talk about FRBs. So on the left-hand side, on the right-hand side is the same frequency time and this 1/nu square dispersion law from a signal which is now called the Lorimer Burst, named after Duncan Lorimer, who actually first discovered it. But what's actually peculiar about this particular object was that, one, it's extremely bright. It's extremely bright, as in you get a flux of about 30 Janskis. If you observe pulsar, the brightest pulsar we have seen till date gives you 1 Jansky. Okay, and this is a single pulse which gives you a flux of over 30 Janskis, which is about 30 times higher than the normal pulsars which we have seen. The second thing is this pulse width, which is shown over here, is extremely narrow. It's just 10 milliseconds. So it's an extremely short burst of extremely large energy. And this is where things get interesting. The dispersion measure was actually much more than what Milky Way could offer. What that means is that if we actually go back to this diagram, we know we are over here, and let's say we were looking in this direction, somewhere over here. Okay, if you start integrating this equation, if you know the electron density model, and if you integrate till the end of galaxy, you'll get some dm value. But the dm observed for this particular transient was much, much larger than what Milky Way could offer. And since we know that dm is a proxy for distance, this means is that this object is this particular transient signal is coming from out of our own galaxy. So this was the first astrophysical signal which came out of our galaxy, which was extremely narrow and extremely bright. Now, you remember luminosity has this d square term in it, and d is the distance to the object. That means this event would have been extremely bright wherever it was, because you were able to see it at 30 Jansky, so far away. Okay, So that's and this started the field of FRBs, or fast radio bursts, in 2007. So let's look at what the signal journey of this whole of the FRB looks like. So there's some galaxy, as I told you, these signals are coming from out of our galaxy. There are other galaxies which host these signals. So there's some host galaxy, and that produces the FRB, and then it has to travel through all these things which I'll talk about now. And what you observe is only this dispersion sweep over here, and this dispersion sweep has this 1/frequency squared curve actually gives you has many components to it. So when the FRB originates, we do not know how they originate. Whenever they or wherever they originate from, there's some electron density from the FRB engine, whatever is generating the FRB, and the free electrons in the host galaxy itself. So those are the contributions from the FRB engine and the galaxy itself, and these are a function of redshift because they are at a distance, and redshift is given by z. Now, it may happen that your galaxy is in a galaxy cluster. That means there's a whole cluster of galaxies, and then that cluster will have its own interstellar medium. It's called the intercluster medium. So you'll have so that means you'll have free electrons which are in between those galaxies, which will be given by DMICM. It may also happen that when your FRB signal is passing by, it's passing through a galaxy. So in that case, the electron density or the free electrons from that galaxy will give you a contribution. So that's called the circumgalactic medium. And then there's all the medium which is between your galaxy and our galaxy, or whatever the host galaxy it is. It's called the intergalactic medium. And then when the signal finally enters the Milky Way, we have contributions coming from our own galaxy, which is the DM Milky Way over here. Now, so what you observe is just this DM observed, but it has all these contributions in between, which you have to sort of take care of. And this is where all the fun science part comes in, because you can probe the universe using all these quantities over here. Now, let's talk about how the field of FRBs have evolved over since 2007. And what I want you to see over here is how fast sort of discoveries have come up and how fast this whole field is evolving. So in 2007, we had the Lorimer Burst. This is the first FRB which was discovered, the first extragalactic, extremely fast, extremely bright event. And then for about 3 or 4 years, or actually, yeah, for about 3 or 4 years, there was nothing. People were speculating whether these objects are real or not, whether something man-made could cause this or not. But anyway, in 2011, we had another FRB. It's called the Keen Burst, after Evan Keen, who actually discovered it. And after this, we stopped naming the FRBs after the person who discovered them. In 2013, we discovered 4 more FRBs, and these are just the pulses from those FRBs. This is the flux density, and as you can see, these are slightly weak. These are about 1 Jansky, half a Jansky, or so on. But we were able to now basically start looking at weaker and weaker bursts. In 2014, we had a detection from the Arecibo telescope. So this was the first FRB which was detected from Arecibo telescope. Until now, from 2007 to 2013, all the FRBs were from Parkes telescope, which you can imagine will lead to more scientific questions like why only Parkes radio telescope down in Australia is discovering FRBs and none of the other radio telescopes are. And this was answered in 2014 when we actually found the first FRB from the Arecibo radio telescope. Now, in 2015, we had the first real-time detection. What does that mean? But what this means is that we now had codes which will de-disperse this data and look for the signal in real time. That means it will. So if an event happens, you will know it as soon as it happens, and that's what is real-time detection. So in 2015, we had pipelines which were able to do real-time FRB searches. In 2016, we detected another FRB from the Green Bank Radio Telescope here in West Virginia. In 2016, something interesting happened. This was also the time when I joined Ph.D. We found that the FRB which was discovered at Arecibo is a repeating FRB. It was weird because up till now, all these FRBs were one-off bursts. We just saw them once, and we spent huge amount of radio telescope time looking at if you see an emission from those things again, and we never did until 2016. And there was only one FRB which gave you repeat bursts, and that was also very sporadic. So it will give you bursts at some time, but you cannot predict when those bursts will come. So that was 2016. In 2017, what happened was, since the FRB repeats, you can actually localize it. And what do I mean by localization? So here so the FRB was discovered using the Arecibo telescope. And if you look at this circle over here, this is just the sky map. This is RA and DEX. So this is, if you look at the sky, this is how we map the sky. And then these circles over here, these represent the beam size of Arecibo radio telescope. That means how large of a sky you will see. That means you this whole part of the sky, you will just see it as one dot. And if you start looking through Arecibo. But then we also have interferometers. These are just an array of telescope. Looking at it using interferometer, you can make an image when that source was on or when it was emitting and pinpoint where exactly it was. So we actually pinpointed it in 2017, found that this really small dot over here is the FRB. It is coming from a really small galaxy. And to do two things. One, find out that the FRBs are actually coming from another galaxy. And second, now, since you have a redshift of the galaxy, you actually know for sure that these are extragalactic objects. These are not coming from our galaxy. These are coming from galaxies which are other than Milky Way. Now, in 2018, there's a telescope in Australia called ASCAP. They said, hey, we have this telescope, and these are all dispersed. So about 2018, we had about 50 FRBs or so. And this is about 10 years of FRBs. And in 10 years, we got about 50 FRBs, especially adding 20 FRBs by the ASCAP telescope in Australia. And now, start looking at how fast things are evolving. In 2019, January of 2019, there's another telescope called CHIME in Canada. It's like, hey, I have another repeater, which was a big deal because up till 26, up till from 2007 to 2016, we had no repeaters. In 2016, we had our first repeater. In 2019, CHIME is like, I have another repeater, and here are 13 more FRBs. I was like, okay, great. In June 2019, we now have capabilities that as soon as an FRB occurs, we can actually localize it in real time. So first was real-time detection. Second is real-time localization, knowing and pinpointing where the FRB is actually coming from. So this is another result from the ASCAP telescope. This is the galaxy where FRB is coming from, and this circle over here is the location of the FRB. And there's this another telescope called DSA, which is Deep Synoptic Array, did the same thing, but the resolution is not that great as compared to ASCAP, so their localization is slightly poor, but that's all right. We now have real-time localization capabilities thanks to many upgrades to these telescopes in just a couple of years, actually, from 2017 to 2019. In August of 2019, CHIME is like, I have 8 more repeaters. In January of 2020, people use another interferometer to localize the second repeating FRB. So this was the second repeating FRB which CHIME gave in 2019 January. Within a year, we localize it, and it's coming from a spiral galaxy. So here's a spiral galaxy, and this red dot over here, which is a zoomed version of here, is the location of the FRB. In January this year, CHIME is like, I have 700 FRBs in preparation, and I'm going to release them soon. And added 999, how this is going. But this is not over yet. In January 2020, CHIME is like, you remember the second repeater? That is actually periodic. There's a 16-day periodicity. That means after every 16 days, there's some emission from that repeater. So earlier I said that, hey, we do not know when the repeat bursts will come, but it turns out there's some periodicity over here. What I'm showing here on the x-axis is the time, and on the y-axis is just exposure, which you don't have to worry about. But these gray bars over here tell you when the FRB should be emitting. and the red and the green triangles tell when the CHIME telescope actually detected something from that FRB. So it was like, okay, the second FRB shows a 16-day periodicity. And then in March, FRB 121102, this is the first FRB, which was found to repeat in 2016. And this is the work which I was involved in. We found that it also shows a 160-day periodicity. So this is the same thing. You have the time on the x-axis. This is MJD. This is modified Julian days. So each unit is actually a day over. Like each number over here is a day, and then these orange bars over here show when the FRB should be on, and there's all these crosses and dots over here show when we actually detected the FRB emission. So it's like, okay, so the first FRB itself is also periodic. I was like, that's nice. In April 2020, things changed. And things changed in a drastic way. And the way it changed was, there's a source called SGR 1935 plus 2154. You don't have to worry about the name, but it's a neutron star in our own galaxy. And it gave a FRB like 1.5 megajansky bursts. We have never seen something so bright in our own galaxy till date. The sun, if you remember, was 10 kilojansky. This is something which is megajansky, which is 10 to the power 6. And we detected bursts from this, which gives us some clues that maybe sources like these are FRBs, which are in other galaxies. In May 2020, we had something called the Macquarie Relationship. And what Macquarie Relationship is something like this. So you remember you have DM, which is Dispersion Measure, which is a proxy for distance. That means there should be a relationship between the DM and the redshift of objects. And that's what exactly this relationship is. It's called the Macquarie relation. And we were able to find out what exact relationship or what precise relationship actually is there. So that means once you now observe an FRB, you know what DM it is at, you can actually just tell you, you can actually just infer what the redshift of that FRB would be, or how far that FRB is coming from. So what's the story so far? To date, we have about 160 published FRBs, and out of that, 22 of them repeat. And this is what the sky distribution sort of looks like. These are all the FRBs from different telescopes, and what it looks like is they're sort of isotropically distributed. That means there's no preferred direction in which you should be looking for FRBs. Like, okay, we have 13 localizations now, and out of those, 3 are repeaters. And these are some of the localizations, and they actually come from a very, very huge variety of host galaxies. So this one is a spiral galaxy. This is an elliptical galaxy. There's a dwarf galaxy over here. These are just 5 of them. There are 13 of such. There's a huge amount of spectral variations, and by spectral variation, I mean this is the frequency. This is the time, and you remember that 1 over frequency squared law. This is corrected for that. Even if you correct after that, what you see is FRBs emit in a very weird way. For example, in this case, there's no emission in this part of the band. There's only emission in a really small part over here. This is present in most of the band. This is present in very small parts of the band. And this just shows some random patches. But this is not limited to just one particular telescope. We have seen this from many, many telescopes. This is all again corrected for dispersion. And then there's something also which we measure, which is called polarization of the electromagnetic signal which we are receiving, but I won't get into that. That's slightly more involved. So that's where we are in terms of FRBs. We have more than 55 theoretical models for these objects. Up until 2018, the number of FRBs were less than the number of models which were there to explain FRBs. Here are just some of the models which I've listed. I do not work in FRB sources, so I won't really comment on that. But moving on, the question which is the second part of the talk is how to find them. And let's address that, like how to find FRBs. And the thing which you have to do is it's a 2-step process, more or less. Get some radio data. So here we have the Green Bank telescope. It's pointing at some part in the sky. And you run a FRB search pipeline. But what do FRB search pipelines actually do? So let's look into that. What you record is this thing in the middle, which is the frequency time data. So here's the time, here's the frequency. Here's the highest frequency, which is at the bottom, and the lowest frequency, which is on the top. Okay, so this is inverted. In this case, we actually know that there's an astrophysical signal because you can actually see it here. And a priori, you do not know what DM or what dispersion measure the signal would be at. So what you do is you de-disperse your data at many trial DMs and you look for peaks. So we found something called a DM time plane. So this is the dispersion measure, the trial DM at which you'll de-disperse your data, and then this is the time. So at 0 DM, that means you do not do any de-dispersion. If you just add up all the frequencies, this will give you this top time series over here, which is just shown in color in this part. You de-disperse it at some other DM, you start correcting for that, and then you'll see that this signal starts to line up. There's a faint signal over here, and this corresponds to this part over here in the DM time plane. When you are at the right DM, in this case, it's about 56, all of the signals in the frequency line up, and when you add it up, you'll get a really huge peak. And then this is fairly strong signal. This is what we keep looking for, and then so on. And in the end, you actually look at candidates like this. You have data, you de-disperse it at many DMs, and then whichever DM gives you the maximum signal to noise or the maximum peak versus this difference, you just start looking at those candidates. But you would think that, yeah, life is that easy. It's actually not. What you end up is looking at things like this, which is called RFI. This is radio frequency interference. This is all the noise which is man-made, mostly through things like Wi-Fi routers and Bluetooth receptors and radars. It looks like FRPs because it gives you similar things, but it's actually not. It's actually man-made. And this is much more often the scenario than actually finding a real FRP. Now, what are the issues when you start looking at FRP or when you start searching for FRPs? And the answer is there's a huge amount of candidate rates. So the Green Bank telescope I just told you about, that gives us about 1,000 candidates per day. Our Arecibo telescope used to give us 4,000 candidates per day. We are unsure of its future right now. The Very Large Array, this is an interferometer. This gives you about 10,000 candidates per day. And you see, all you have to do is basically look at a plot like this and just tell me whether it's real or not. So it's going to take you about a second worth, or it's going to take you about a second to tell you whether it's a real signal or not. So if you have an army of and doing this, even then you cannot. Reason why you need a system which will take care of or want to follow it up with other telescopes, and that's why that's where all the real-time detections also come in. You can have real-time detections, but then you need to look at candidates in real time as well, and then alert other telescopes that, hey, I found something in this direction, point there and see if you can also see something else. So you have to point your optical, your X-ray telescopes in that direction to see what if they can see any other emission. And if you see some emission in other wavelengths, you will be able to better constrain the theories of FRBs, or why these signals, or where these signals are actually coming from, or what are the origins of the signal. Now, the solution for all this is we make machines do it, and that's where all the machine learning part comes in. So just before I guess I get into machine learning, I just wanted to show you this graph, which I made I think last year in October about this time, which shows the rise of machine learning and deep learning in astronomy. This is the number of ADS abstract which have the word either machine learning or deep learning in it. That means they've used some technique. And these are just some of the machine learning techniques. This is the first GPU neural network. And then PyTorch and TensorFlow are just two of the sort of prominent frameworks which everyone uses to make these neural networks. These were open source in about 2015 and 2016. And since then, this field is just booming up. Now, what we're going to talk about is neural networks. And before I get into that, are there any questions?
Yeah, I have one question.
Yep, go ahead.
Yeah, so how do you distinguish between quasars and fast radio bursts, is there like even that is a really like loud radio source, right?
Yes, but quasar emits continuously. It doesn't give you a really narrow pulsed emission.
Oh, okay, yeah,
Like it
right.
never stops emitting.
Okay, yeah, got it.
Okay. Okay, so we'll talk about neural networks now. And if there's something which you want to take away from this talk, is that neural networks are not magic. They're just a non-linear mapping between your input and your output. So we know about mathematical mappings. You have some domain, or anything which is connecting two domains is called a mapping. In this case, let's say you just have some input, just three numbers, x1, x2, and x3. These could be any numbers, 1, 2, 3, or 1.2, 2.3, or something like that. Any numbers. You create a non-linear mapping between this number and y, which is just single scalar. And that's essentially what a neural network is. And this non-linearity is very important. This is at the heart of neural networks. And the reason you need a non-linearity is because if it was a linear thing, if we could write it as y is equal to mx plus c, or some combination of that, you don't need a neural network in that case. You can just write a linear function and be done with it. So that's why these are non-linear mappings between your input and your output. And that's what neural networks are. And what happens in a neural network is the very basic unit is called a neuron. So this is very similar to our biological neurons. And what you do is you take your inputs. These were just some numbers, x1, x2, and x3 in this case. You multiply it with some weights, w1, w2, and w3. And you add a constant called bias. And then you pass it to an activation function. And this activation function is what introduces non-linearity to your neuron, or to your neural network in the end. So this is a very simple neural network with just one neuron, three inputs, and one output. You take this dot product, add a bias to it, and this becomes an argument to some function. And this is what some common activation functions look like. Is a sigmoid. This is the hyperbolic tangent, and then the rectified linear unit called ReLU. And the reason these are called non-linear functions is because is as follows. So if your input was, let's say, for the sigmoid function was 4, you'll get an output of 1. But if your input was 6 also, then also your output is 1. That means once you have an output, you can never go back to the input. You can never figure out what triggered that input. That means if your output is 1, you can never know whether the input was 4, 4.5, or 6, or anything greater or less than that. And that's why these are linear, non-linear functions, because you can only go in one direction with these guys. You can never go back. So, and what we do is we connect many neurons together. So all these blue circles in the center are the neurons. All the orange arrows are the weights. And then you apply the same operation for all of them. Here, this will get inputs from x1, x2, and x3. There'll be some weights, there'll be some activation function, and then this will give you one number. And then you do the same thing at the end. And this forms a hidden layer. You can add another hidden layer. And what this does is it increases the capability of your neural network to learn more and more complex features. So if you want to learn something which is heavily complex, what you'll do is you'll increase the number of neurons and you'll increase the number of hidden layers in your network. And this will learn the non-linear mapping between x1 and x2. You don't have to define the mapping. That's the whole point behind all this. Convolution neural networks. So in the previous image, what we saw was all the neurons are connected to all the other neurons in the next layer. So that means this is connected to all three of them, this is connected to all three of them, this is connected to all three of them, and so on. And the same thing happens over here. And as you can imagine, the number of connections will grow exponentially if you have a large number of hidden layers or a large number of neurons. What we do for images is instead of connecting everything to everything, we just connect the adjacent ones. So we do an operation called convolution, where you just take these two and you apply the same function over here. There's some weight over here, there's some weight over here. You multiply the weights and add them, and then give them as an argument to the convolution to the activation function. Then you get some output. So that's what is used for working with images. And here's an example. There's a picture of a person over here, and this red 3x3 matrix over here is what is called your convolution kernel. And these are the so these bigger boxes over here represent the values from the image, and the smaller number over here represent the value from the kernel. This is what is there in the red 3x3 matrix. And what you do is you multiply the value from the image and the kernel, and you add all of them up, and you get the resultant image. So in this case, what it's doing is it's trying to find all the basically horizontal features in the image. So, for example, features like this, like the eyes, and so on. And you apply many such convolutions to extract features from the images, and then ask your neural network to learn to classify that. And we'll see that in slightly more detail. So here's how a convolutional neural network sort of looks like. Here's a handwritten digit 2. You take this digit, you apply many small convolution kernels over here, and that gives you some resultant images. You apply more kernels over it, and more kernels over it, and more kernels over it. And the whole aim of applying more and more kernels is to extract more and more features out of this image. And then you finally map the output of these features to digits between 0 and 9. And that's how you basically make a really simple neural network to classify handwritten digits. Now, this is how I'll start representing the neural networks now. So what's shown over here is something similar to this. Here are the dimensions of the image, and this is what is written over here as well. So this is 224 by 224, and then there are 64 kernels in the first layer, and then there's another layer of 64 kernels, and this red box over here, and that sort of gives you the activation function, because you remember you have to introduce non-linearity in your system. And then you apply more and more convolution kernels, you extract more and more features, and then finally this part over here, this purple part, this is similar to this, where everything is then in the end collected to everything, just to classify what's the output like. So we take a very simple network. This network is actually called VGG. This is from the Oxford University's Visual Graphic Group. We take an image of a cat and see and we'll see what features does this neural network extract at all the different stages. So the very first stage, this is the result of all the convolutions on the image of this cat. So you can see in this case it is extracting some features, and in this case it's extracting other features. So what the neural network sort of learns is how to identify features like eyes and nose, and then different shapes, and so on. So this is the very first sort of convolution layers. If you go ahead, you can see you're extracting more and more features, but the features are also starting to become a bit abstract. Like here, you can make out it's a cat to begin with, but it's becoming harder and harder in these images to find out, to actually find that this was actually a cat through which we begun. If you go down further, this becomes like a QR code. This is something which we as humans cannot understand, but the neural networks have learned how to map these features to something called a cat or a dog or something like that. Now, this is exactly what we do to look at our candidates as well. So this is that DM time plot. This was the DM over here and time, and then this was the shape which we were looking at. This is the correct DM at which you'll see the maximum signal to noise, and so on. And this is the same VGG network. I did not change anything, just the same image. Instead of putting a cat now, we put the image of our image from our candidate. And you can see it's extracting different features. It's extracting lines at different angles. It's extracting vertical and horizontal features. Some things are concentrating at the center. Some things are concentrating away from the center, and so on. So that's what we have in the first layer. You do the same thing. In the deeper layer, you extract more features. And finally, it again becomes like a QR code, which the neural network learns to map between what is a real astrophysical signal versus what is RFI, which is man-made. And hence enter fetch. So fetch is a set of neural networks which takes in your candidates and then tells you whether something is a real FRB signal or it's RFI. So it has two such neural networks, and then they're connected using some smart techniques, but you don't have to worry about that. And this is some work which I led during my PhD about 2 years ago. It takes in your data and just tells you whether something is real or not. And the way it was made was you take the first frequency time. This is the de-dispersed frequency time data. So this is the same data just coming from telescope, but except it has been de-dispersed at the FRB signal. you choose a neural network and you train and you say, hey, these are the signals which look like FRBs, these are the signals which look like RFI, learn that. So you train that. You choose another network, do the same thing for the DM time. This is that bow tie sort of shape which we talked about. You train this network and then you combine them using fusion. We can talk about that later if people are interested in that. And then train the combined network, and then gives you and that gives you the full model which tells you whether something is real or not. Now, in terms of sensitivity, let's see how it does. So the first thing is this is completely agnostic of telescope and frequency. That means it doesn't matter which telescope the data is coming from. It doesn't matter if it's coming from a telescope in India or a telescope in Australia or a telescope in US. It works for everyone. And the other thing is its performance. So recall is defined as the number of FRBs which you detected versus the number of FRBs which you injected. So if there were 1,000 FRBs in the data, we will only miss 5 out of 1,000 FRBs. That means you can find 99.5% of the FRBs in your data, and that's the performance of fetch. But let's talk about performance on real data. So when we published fetch, there were 33 FRBs from ASCAP, and as you can see, we have 11 neural networks, and most of them found all of the FRBs. But this is not the impressive part. The impressive part actually comes here. So this is the RFI candidates. This is all the false positives which the FRB search pipelines give us, and these are about 10,000 of those, and out of which fetch misclassified less than 50 in each case. In this is our best model, the model A. It found all the FRBs. It only misclassified 2 out of 10,000 candidates. That means it only misclassified 2 candidates saying these are FRB when these were not FRBs. And then there were 8 FRBs from Parks, and all of our model found all of the FRBs from Parks. And then this is another FRB from Green Bank, and most of our models find everything. So that's fetch. And since its publication, we have searched more than 2 million candidates from all these telescopes all around the globe, just proving our point that this is completely agnostic to any frequency or telescope. Now, at present, this neural network is working 24/7 in real time at these 3 telescopes. This is the Very Large Array in New Mexico, the Green Bank telescope, and the Lowell telescope in UK, searching for FRBs in real time. So that means by 2015, we already had real-time FRB search pipelines. That means there were pipelines which can do the FRB search in real time. But now with fetch, you can also do classification in real time. You can actually get rid of all the false candidates and be only looking at all the real candidates. So that's where fetch presently is. But let's talk about speeds. We said we need something which works in real time. Well, fetch can classify more than 60,000 candidates per hour. You remember, Very Large Array would produce 10,000 candidates a day. This can do 6 times that in an hour. So that means we are future-proof as well. And then, since then, multiple people have used fetch to find more and more FRBs and multiple bursts from FRBs. And here are just few examples. You can see these 2 in particular are really weak. These 2 are really strong, but also really wide. The frequency time structure is also very, very different. This is only this is only present in a really small part of the band, and so on. So we have been able to, using fetch, we have found many FRBs and many bursts from repeating FRBs as well. This basically makes life easy for many people who don't have to now sit and look at candidates for hours, days, weeks, and months. Okay. Now, let's talk about FRB searches and how FRB searches are actually done. Now, initially, FRB search was done on archival pulsar data. So what people did was they looked at a patch of sky, saved all the data, and searched for pulsar in it. So this is the same frequency time data which we talked about in the very first slide. And then people did FRB searches on that, but that got over pretty quickly. This is where the Lorimer Burst, the first FRB came from. The 4 more FRBs, which were later in 2013, came from archival searches. The second thing is we know that galaxies give us FRBs. So it will make sense that if you point your telescope towards galaxies and hoping that, okay, if I record it for long enough, I'll get an FRB someday, which is good and perfectly fine, except getting telescope timing is hard because you have to compete with everyone else who also wants telescope time, and telescopes are not, and then you have to share your resources with other people in the community as well. So what we do is we go to the last bit, which is called the commensal searches. Here, what we do is we let the observer choose where do you want to point the telescope, because they can do whatever science they want to do. And what we'll do is we'll take a copy of their data and we'll run a real-time search pipelines. And these are called commensal searches. And we'll talk about them now. So first, let's talk about targeted searches. So this is some work which I was involved in using the ASCAP telescope in Australia. It's like, okay, we know that FRBs come from galaxies. So let's look at a galaxy cluster. So this is a cluster of galaxies. That means there's a huge amount of galaxies in your field of view. And then a large number of galaxies would mean that you might get some more FRBs as compared to looking at any other piece of sky. So what I have on the right-hand side is the X-ray image of the Virgo galaxy cluster. This black blob over here is M87. This is the same supergiant galaxy which has a black hole in the center, and people used this Event Horizon Telescope to map to take an image of the black hole. This is the Coma cluster over here, and there are galaxies which are actually not visible in X-ray, but actually in there. So we did a 300-hour survey. We pointed in this direction for 300 hours looking for a FRB, and we actually found one. So we actually found FRB. It's called 180417, based on this is year, month, and date of discovery. This is the dispersion measure 474. If you look in that direction, our own galaxy will only give you a dispersion measure of about 30-ish. So that means the rest of the dispersion is coming from all the other sources. Now, in this case, what we actually found was that the DM of the FRB was, of course, greater than Milky Way, but it was also greater than what the whole Virgo cluster can give you. That means that the FRB is coming from behind the Virgo cluster. That has some implications, but let's not get into that. We did a multi-wavelength follow-up. So this was before before fetch was actually there. So that means this was a time when I had to sit and look at candidates by eye manually every day for about a couple of months. But then even then we were good enough. We were fast enough that we got the telescope time on Parkes radio telescope that night itself. And then we followed it up with other telescopes and optical telescopes as well, but we did not see any emission. So that means this is not a repeating FRB. This is just a one-off event. Now let's talk about green burst. So what green burst is, it's a commensal pipeline for searching for FRBs using the Green Bank telescope. And what happens is, this is the Green Bank telescope at the in the background. This is a 110-meter dish. And this is what the optics look like. You have all the waves coming. They reflect off the primary dish. They go to the secondary dish over here, and then this is where all the receivers are. So this is what the radio receivers look like. There are slightly different version of what the receivers in your phones or your old radios look like, but the principles are essentially the same. And this is what we do. We take a copy of the data, we run our real-time search pipelines on it, and this is how sensitive we are at different wavelengths. So you remember FRBs are of the order of several Janskys. The minimum we can see is something like 0.14 Jansky. So we are extremely sensitive thanks to the large telescope surface area, and that's what green burst is about. We are commensal since April 2019. That means to date we have seen we have searched for more than 6,600 hours of data, and all of this data is searched completely in real time and in a completely hands-free way. But what I mean is that there's a pipeline which we have built. It takes the data, it searches on all the DMs, it searches for the FRBs, and then whatever candidates it gets, it gives it to fetch, and then once fetch says something that yes, this looks real, only then we get a message. So you don't have to sit and look, oh, whether the FRB occurred or not. We'll come to know about if an FRB has occurred. Now, to date, we have used Green Bank telescope to look at pulsars as well. So we have seen more than 2,000 pulses from 20 different pulsars. People have observed FRBs, and we have detected all of them in real time. So this is one FRB. It is 190520. As you can see, this is present in a really small part of the band, and this bunch over here is just RFI. and we found this in real time. But using all of this, we can also put some kind of an estimate on what is the rate of FRBs, or at what rate these events are happening. So if you have a telescope which can look at a minimum of 1 Jansky, this telescope would be able to see about 1,000 FRBs per day if you were looking at the whole sky. But the radio telescopes, they look at really small part of the sky at once, and that's why the number of FRBs that you see is so small. But anyway, the other pipeline is called George Search, which is similar to Greenberg. So this is the George Bank telescope, 76 meter in diameter, in the UK. Similar pipeline, single beam, just uses one GPU, which is GTX 1080, completely hands-free. As soon as you find something, it will give you a lot of Slack. There's also real fast. So this is a pipeline on the Very Large Array. This is in New Mexico. It's a series of 27 such dishes. And this can actually do real-time localization. That means it can form an image and find where the FRB was in real time. And all of these telescopes are using fetch and finding FRBs in real time. Now, in conclusion, we have FRBs. They're extremely bright and extremely fast objects. We do not know what's causing these objects or what's causing these events. We need machine learning techniques for all these prompt discoveries. But also, there's a huge variety of things which we have seen. There's a huge variety in spectra and polarization in host galaxies. That's there. There are these are open questions which we do not have the answers to. Are there two populations of FRBs? Are there two kinds of FRBs? Ones which repeat and ones which do not repeat? The rate estimates which we are putting, do they actually make sense? And what does the luminosity distribution of these FRBs look like? And lastly, what are the sources? What emission mechanisms can cause these extremely bright events? Well, but the future is bright. We have about 700 FRB catalog coming in any day now, and our telescopes are now capable of doing real-time localizations. So more and more things are coming, and that's where I'll stop, and I'll take questions now.
Hello.
Yep.
Yeah, I have a question. So, in various APIs such as TensorFlow, Keras, and stuff, there are various optimizers, like optimizing methods.
Yep.
And you have to choose between them. But usually, when we search, usually the answer is that it depends on your data which optimizers are supposed to be used.
Yes.
So in in these FRBs, which optimizer is used, or
Adam.
multiple are used?
No, Adam. We use Adam.
Okay.
Adaptive momentum.
Okay.
Are CNNs more reliable over the? Wait, let me open that. Okay, are CNNs more reliable here over RNNs? Yes. The reason is that we are working with images, even though these are time series images, but each event is independent of another event. Since events are not linked to each other, that's why you really don't need to use an RNN over there. So if there's some correlation, like if your next event is dependent on the previous event, it would make more sense to use the RNN in that case. In this case, these are independent, and also these are images. So that's why we use CNNs. Yep. Yep. Yes. So what you're looking for is not the same emission or the same burst. What you're looking for is something like an afterglow. or emission which happens after the event. So, for example, there are few theories which say that maybe these are associated with supernovas. So, if it's associated with a supernova will give you an afterglow which is extremely bright, I guess, a day after it happens, and then it just fades. So that's why you need. That's why you're looking at multiple wavelengths with other telescopes to see if there's some other emission which is associated with the FRP. The other thing which I also want to point out is related to dispersion. So you have this delay over here, right? So this delay goes as 1 over frequency squared, and what that means is that if you're observing at extremely low frequencies, this delay is very, very large. So if you're observing at 1 gigahertz, the delay between the signal here and the signal at 100 megahertz is about 10 minutes. So if you can point a telescope, if you're observing at 100 megahertz and you can point a telescope in less than 10 minutes, then you will be able to catch the same signal. So those are two things which you sort of take care of. So these are one-off events. Usually, like, there's been rarely a case when you saw the same event at multiple telescopes, unless you were specifically looking with multiple telescopes at a particular part of sky, looking for FRPs. But other than that, there's no particular way. What I will tell you, in fact, is something like this. We go here. Yeah, here. So this is the number of beams. So ASCAP makes like 36 beams on sky. And when an event occurs, so the FRP which I talked about, which we detected from ASCAP, occurred over here in this square box over here. But since you have multiple beams, it was detected in all three of them. So that gives you some more confidence that this is an astrophysical signal rather than something which is RFI. But it depends on telescope to telescope. There are ways of confirming it, but it's heavily telescope dependent.
So I had another question. Like when like there are some false positives, right? So so earlier you said that astronomers had to filter them out by manually filter them out.
Yep.
So how does that process work? Is that analysis of data, or
it's literally just looking at basically images like this versus this.
Yeah.
That's pretty much it. You know what actually RFI looks like. Please see. I can probably show you some more things. You can still see my screen, right?
Yeah, it's your desktop.
It should be showing you Slack right now, I guess.
Yeah.
Yeah. So that's all the candidates from Green Burst. Very good. And this is what literally RFI looks like. So that's pretty much it. You sit and look at candidates which look like this. Versus there must be some actual. Yeah, this is some actual signal. This is what a real one looks like. So someone was observing a pulsar. This is what the real signal sort of looks like. Someone was observing 0355 plus 54. And this is what like an RFI looks like. This peak over here is just because this extremely bright pixel over here at the very end. That's RFI. Similarly, this. Oh yeah, here. So this is the one from Jodrell Bank. It's similar kind of candidate. This is extremely weak. You can barely see it, but it's actually there. This is a strong one. And this is what it literally looks like.
Okay. Thank you.
Yep. 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 The detection is, so the detection is actually done using match filtering, but even match filtering leads to all these R5 candidates. Yep. But the detection is actually done using match filtering. Yep.
If there are there any more questions? Okay. Devansh, can you share your journey in IISER and after IISER, and what should we expect after IISER, like after our graduation?
Okay. Well, so I joined IISER in 2010, and that was back when we were in the CET campus. I don't think any of you were there. I think all of you just came to Wipro directly. Is that right?
I guess fourth or fifth years have been in CET campus.
Okay. Yeah.
They had
Well,
labs in CET campus.
okay. Well, anyway, so yeah, so I came in 2010, and I don't know, it was, I guess, average or below average. In IISER, my GPA was like 7.2 or something, so yeah, I was never into this GPA stuff. Mostly did whatever I wanted to do. I mostly studied courses which I wanted to study, and then never sort of paid attention to others. And while that worked out for me, it may or may not work out for everyone. I took physics major because I was interested in Astro. Also, I was a KVPI fellow, so I had to do summer internships, and that was, I guess, the best part of my 5 years at IISER. So during my first year, I went to Delhi to work at Nebula Planetarium. In second year, I went to Aries in Nainital, that's an optical observatory. In third year and fourth year, I went to NCRA in Pune to work with GMRT, and then that's pretty much it. And my master's thesis, I was working with Archana, who is now at IIT Bombay. So I was working on pulsar timing arrays. So this is using pulsars to find gravitational waves, and that was a fun project because I proposed it. I was like, "Hey, Archana, I want to work on pulsars," and Archana's like, "Yeah, but I only do gravitational waves, and I do not do pulsars, and I'm not open to doing pulsars anymore." I was like, "Okay, fine. We'll find something to meet in between." And then I sort of came up with a project. And then Archana was kind enough to sort of accept that. I think, are you guys now allowed to go out of IISER to do your major projects? That's sad. That's sad, actually, because I know other IISERs allow it. Anyway, by the way, that interferometer might be still around in some storeroom here. That's good to know. Yeah. Anyway, so that most of my time IISER went in, I don't know, doing random shit. I really like cooking, and although it wasn't allowed in hostels, that's what I was doing most of my time. I was either working or cooking something nice. I don't know what things people do in hostels these days. Also, this was the time when smartphones were just coming in, so all these games and video chats and things like these were not there at all. So much simpler times, I guess. So after IISER, I took a year to stay there and work with Archana and work on the same project I was working on as a project assistant, and then I applied for Ph.D. And I got here in the US. One thing which I think IISER does not prepare you well for is if you want to step out of science at any point. It's good if you want to do a PhD. It's really good. It will give you huge amounts of exposure. It will It will connect you to a lot of people. It will tell you how to do research really well. And that's something which I really appreciated about IISER. And that's something which you'll appreciate once you're out of IISER, more specifically. But one thing which it does not prepare you for is if you want to get a job right after IISER. So if some of you are thinking of jobs right after IISER, you would have to work on your own. That's something which I'll sort of look out for. Like really think about what you want to do after IISER, and if the answer is a job, then start working for it right away. But if your answer is PhD, I mean you're really on the track already, so you don't have to do anything else. And then in 2016, I came in here. The other thing is, if you're applying to US, you will have to do a lot of coursework. But since with IISER you get a master's degree, the coursework is much easier than IISER's coursework. So if you have been through IISER's coursework, which all of you, and I'm sure will, the coursework anywhere else will be like a piece of cake. That's another nice thing about IISER. And I came in here, did all the coursework, started working with Duncan Lorimer, Maura McLaughlin, and a couple of others, and sort of in 4-ish years I finished my PhD, which is nice. The thing which IISER doesn't allow you to do is to step out of science, which you should be really careful about, because for my PhD, I had to do a lot of technical things. So I had to learn machine learning on my own, on the fly. There were no courses anywhere. I had to learn how to use GPUs. I had to learn how to do programming. But I knew programming back when I was in IISER as well. And that's something which you really need to figure out on what you want to do, and then take it there. I'll be happy to answer questions if people have specific questions regarding to, hey, this is what I'm thinking about doing in like next couple of months or a couple of years or so on. What other programming languages does one need to know the field of astronomy or physics, and how much in depth? Okay, people in astronomy heavily use Python. Okay, that's part one of it. Part two is most of the astronomers are not world's best programmers, and that's fine, because you're not doing a computer science degree, you're doing physics and astronomy. So that's okay. The question is how much depth is really dependent on in what field you are exactly. My interests are a bit more technical. I know half a dozen of languages. I use more or less 2 or 3 languages every day. So my job is slightly different. Some people are more physics oriented. I am more tech oriented in terms of that. Like in my case, I really care about finding FRBs, finding more and more FRBs, finding them fast. And that's why I'm more tech oriented. What I really don't care about is what happens once you have found an FRB. And there are people who do science with once you have found an FRB, what all science you can do. So if you're in the depends on which side you are. If you just want to do science with FRBs, you really don't need to know a lot of Python or a lot of any other language. Also, things are becoming much more easier in terms of learning a language and getting help with that. Stack Overflow is huge now, which wasn't the case, I guess, when I was learning all these things. There are tons of tutorials available on YouTube and everywhere else. There are tons of things on Coursera and Udemy and things like that, which were not like, I think edX started while I was in IISER third year or something. Coursera was there, but the number of courses which they had were really handful. I think they had about 100 courses, and out of those 100 courses, a lot of them were humanities and arts-based courses as well. So not a lot of technical courses which I could have used back then. So I just had to go to books and then learn things on my own, which was fun in its own way. But now there are a lot more resources. With COVID, I guess things have changed a little in terms of internships. I do not know what happened to like this summer. People usually go for summer projects. What happened this summer? Did people just do it remotely? The people didn't do it at all, or what were your experiences like?
Some of us are doing it online, and
Okay.
I guess like the which doesn't require lab work or like I am doing right now internship like under a professor in NICER.
Okay.
And it's basically work on Alma archives on protostellar disks.
Okay.
So I've been using CASA.
So yeah. So you know
CASA, yeah.
the
CASA,
painful
Cassis.
little software to work with.
I'm sorry, I didn't hear you.
I'm saying it's a painful software to work with.
Yes.
The pains of CASA. So the real-time system I was talking about, CASA is used for imaging, and that's what they actually do. They do all of the things which CASA does, except in real time for all DFRB searches. So uh, that's sort of the scale of things which I was talking about.
Mm.
Yep. The other thing which I also have for you guys is I do have a lot of projects which are at the intersection of astronomy and machine learning. So if there are people who are interested in sort of working on these things, I'll be happy to sort of help out. If you need if you want to learn something, if you want to learn programming, if you want to learn machine learning, or if you want to do actual research with these things, I do have projects, and these will lead to publications. So if you are interested in doing a PhD, that's going to be really helpful. Just do let me know if you are interested in more things like fetch or something like that. One thing which you guys surely know is that you need GPUs to work with all of these. And locally over here, we have a cluster of about 25 GPUs. We also have access to the supercomputing center over here, which has B100s and B100s and all the latest GPUs, except A100 for now, at least. I also have AWS credits and so on, which I cannot give it to you, but I can run the codes. So we can technically run on any GPU we want or things like that. So yeah, we can chat about those if people are interested later. Not right now. Yep. So are most of you planning to go to grad school after this, like apply for PhDs, or are you guys actually planning to, I don't know, to look for other kind of jobs as well?
I'm looking for PhD. Like I would like to do PhD.
Okay. In India or outside India?
Abroad, most probably. Like.
Yeah. Well, hopefully things will get better by that time. So you're in third year, right?
Yeah.
Yeah. So by the time you will graduate, hopefully things will get better, and then won't be like COVID. And so do other people have questions, or I don't know, anything about life at IISER? Yep. Oh, okay. So what are you working on? You will be working. Okay. Mm-hmm. I see. I see. Well, that was fun working with Archana. So one thing which I really liked during, I guess, most of my internships as well as working with Archana was the degree of freedom which you get to work on things which you want to work on. For example, like Archana has given you a project. You know what you're supposed to do, but what you're also free to do is explore on your own. Like, hey, these are the new techniques which I know of, or maybe there are techniques, or this is something which I want to achieve out of this. And let's find techniques to sort of apply that or to achieve that. This is something which I really liked during my master project and internship, and that's pretty much what I did during my PhD as well. Yeah, that was, I guess, the most fun part. The other part was that, which I hated during my master's project, was Archana wanted. Archana always put my meetings with her in the morning, and I am not a morning person. I used to like go to sleep at 5 a.m. and she wanted me to meet at like 9 a.m. So there were a couple of times when I missed the meeting, and she got incredibly pissed. But yeah, that was there. Also, so my hostel was right in front of Archana's home, and we used to cook at 3 a.m. or 4 a.m. in the morning with a pressure cooker. So they used to get pissed because of that, because like they're trying to sleep and we are trying to cook. Yeah. Those are the things but the other thing which I did during my master's thesis, which I would recommend everyone do, is don't wait for the end to write your thesis. Whatever developments you do, just take a day out of your weekday and write it up. It doesn't have to be perfect. It doesn't have to be like very well written, but make sure you just type it up. Make sure all the references are in there. And what that helped me do was in the end, it just took me a day to compile my master's thesis in the final form, and that was it. So people have spent typically about a week or a bit more than a week spending, I don't know, going through previous records trying to find what they did, because you won't remember all of that. So just make sure whenever you're doing a project, write it up as soon as you do some significant bit of it. That's going to help you in long run.
Hello. Yeah. So I had a question about GPUs. Like I've been using clusters right now, so I want to learn more about GPUs and other technical stuff. Where should I start, or what are the things I should do?
To get started with GPUs, the first thing you need to know is as follows. You use a GPU when you can parallelize your problem. What that means is that you can run multiple instances of the same thing to get slightly different parameters and get a result out of it. And to actually start learning about GPUs, the place where you have to go to is you first have to learn C++, C or C++. Because that's the interface for GPU programming. And then there are CUDA. So CUDA is the NVIDIA's library for talking to GPUs. And then that just search for like CUDA tutorial or anything like that. NVIDIA themselves have a really nice guidebook which takes you through really simple examples by adding like two vectors together. And then there are basically more and more complicated examples which go in there. But make sure you have, I suggest that you have a problem to begin with, that, hey, this is the problem which I want to parallelize and make it faster. So what cluster are you using right now?
I'm using Slurm cluster.
Yeah, but where is it?
It's an IISER.
And they have a GPU? They have a GPU on it?
GPU, yes, there are. I'll just check.
Do a info that will tell you.
So there are 2 GPU nodes.
Okay, can you log into those? Do you know which GPU? Yeah.
I don't know
Okay.
which one, but yeah, I can use them. I can use them.
Yeah, okay. Yeah, so that's nice enough. Yeah. So you can get started at least. And then, do you guys know about Google Colab?
Yeah.
So Colab has GPUs. You can run CUDA kernels on it using wrappers around it. So there's PyCUDA and CuPy. And those are nice interfaces to CUDA and Python. So if you have, let's say you have an image and you want to do convolution on that, you can write convolution kernel in CUDA by hand and just use CuPy or something like that to just do the convolution with CUDA on the GPU. I think in India they give you K80 GPUs. I don't know which one exactly they give you, but I think it's K80 in India, which is decent.
Okay.
It's not the worst GPU, but yeah.
So main problem I'm facing with the clusters right now is I've on clusters I've been using some quantum chemistry softwares. So
Okay.
so parallelizing they have been already parallelized, and I don't have much to edit them. So
You you never know.
Okay.
More often than that, a lot of simpler things are never implemented just because people didn't have time for it. So you can always find things. That's not an issue. And people do quantum chemistry stuff on GPUs as well. So like I'll say go ahead and search for those libraries first. Like if someone has written a GPU accelerated part for whatever you want to do before writing your own.
So I guess, does anyone have any other questions regarding anything? Okay, I guess. Oh, yeah. Thank you so much for joining us and sharing your experience. And I would like to thank you for taking your time out of your busy schedule and coming early morning actually, given that
I'm
you're
free
not a
now.
morning person.
Yep. I just defended on Thursday, so it's not even a week since I finished my PhD. Yep.
And I'd like to thank the audience also for the participation, and Anvesha, the Science Club of IISER-TVM, for their technical support.
Yeah.
Thank you so much.
Thanks.